The electric field can be difficult to visualize. We introduced the concept of electric field lines, or electric field vectors, I should say, in the previous lecture. However, that's usually not how they're represented visually. So electric field lines will be introduced in this lecture are a useful way of visualizing the electric field around an object. And the two are very similar, but there are differences. So to help visualize the differences, I have plotted here a charged particle Q floating in space in both cases, the same charge. And I have in red shown what the electric field vectors would look like if you drew them around this charged particle. Now the electric field vectors, I have I think 16 or so shown here. I could have a trillion, right? Every single dot is a point in space around this charge. Again, this charge really would be represented in 3 dimensions. The distance, the electric field vector, is an arrow in the direction a positive test charge would be pushed, assuming this charge at the center is positive. And you can see here the direction, again, is away. The length of the vector is representative of the magnitude of the force. So here, when you're close to the charge, r is small, therefore r squared is small, and the force is large, so the vector is big. The further you get away from the object, the smaller the magnitude of that vector, because the force weakens, right? This is an inverse square relationship. If you're twice as far away, the electric field strength is 1/4 as big. If you're 3 times further away, it's 1/9 as big. If you're 5 times further away, it's 1/25 as big. 10 times further away, it's 1/100 as big, and so on. So I could draw a trillion different vectors here to represent what the electric field vectors would look like around this positive test charge, but that's kind of pointless, right? That's not very visually useful. So on the right is how electric fields are often represented using what are called electric field lines. These are not vectors. The blue lines here, and we'll talk about how you draw them and how they are drawn. You can see that the lines emanate from this central charge, and they seem to go off towards infinity. The length of all of these lines, I could continue to draw them out towards infinity if I wanted to. But the magnitude of the electric field depends on the density of the field lines. Where the lines are closer together, the electric field is stronger. As the lines diverge here and they become further apart, the electric field gets weaker. So let's talk about how to draw these electric field lines. So let's talk about electric field lines. A couple of rules in determining the properties of electric field lines, or field lines in general, actually. First is electric field lines originate at positive charges and terminate at negative charges. That means that a field line cannot just appear in space out of nowhere or disappear into nothing. They have to have a starting point, and they have to be a continuous line until they reach their ending point. The starting point has to be a positive charge, and the ending point has to be a negative charge. Now, all lines coming from a single positive charge don't have to end at the same negative charge. There can be multiple negative charges where these lines end at, and multiple positive charges where the lines originate from. But electric field lines cannot start in space out of a vacuum. There has to be something there. The second, the number of field lines that leave a positive charge, so that originate at a positive charge, and the number of field lines that terminate or end at a negative charge is proportional to the magnitude of the charge. That means that there's no set rule in determining how many lines to draw, just that if a charge is twice as powerful, draw twice as many lines coming out of it, or twice as many lines terminating. So if I have a 1 Coulomb charge and I use 8 electric field lines coming out of that 1 Coulomb charge, a 2 Coulomb charge should have twice as many lines, so 16 lines, and so on. Again, there's no hard and fast rule determining how many lines to draw to start, but there is a hard and fast rule to talk about how to handle multiple charges that have different values. If a charge is 3 times as powerful, it has to have 3 times the number of electric field lines originating or terminating at it. The third and probably the most important thing to remember, field lines can never cross. You can never, ever have field lines intersect. You'll never see a field line come in like this and another field line cross like that. This will never happen. Because if you think about it, what it means is at this point where they intersect, the force at that point is in 2 different directions. And it can't be in 2 different directions. If you drop a particle there, it will experience an electrostatic force in a given direction. Right? Right now, gravity is pulling me straight down. Gravity cannot be pulling me straight down and to the side. Right? It can't be pulling me in 2 different directions. The same force cannot be pulling me in 2 different directions. Fourth here, the strength of the field is proportional to the density or the closeness of the field lines. So in areas where the electric field lines are tightly packed together, the electric field is much stronger there, and thus the electric force is much stronger there than when the field lines are widely spread apart. And then finally, the direction of the field, of the electric field, and therefore the direction of the electric force for a positive test charge, is tangent to any curved field lines and is in the direction of any straight field lines. So if you have a field line that's curved, if you have a field line that's straight, let's say that this is your electric field line, if I drop a particle on that line or near that line, it's going to experience a force in the direction of that electric field, assuming that's a positive test charge that I drop there. If the field line is curved and I drop a test charge on it, it does not follow the curve. Right? The test charge would experience a force that's tangent to that line. So at that point, that's the direction of the force. It's tangent to a curve. It's in the direction of a straight line. So let's look at what an electric field would look like, electric field lines would look like around a fairly simple charge, that of a dipole. Now your book has these examples of an electric field around various charged particles. A positive charge in space by itself, a negative charge in space by itself, a dipole, parallel plate capacitor, which we'll talk about in more detail later on this semester. A dipole is simply an electric configuration where you have a positive charge and a negative charge separated by some distance, and they're equal magnitude. So this is some charge plus Q, and this is some charge minus Q, and they're the same. Plus 1 coulomb, minus 1 coulomb, plus 10 coulombs, minus 10 coulombs. They're the same charge, equally spaced. So let's look at what the electric field would look like around these 2 objects. I'm going to draw the electric field in blue. Now the electric field must originate at positive charges. They must terminate at negative charges. And they must give the direction of the electric field of around these 2 objects. So for the first electric field line, I'm just going to draw a straight line connecting the positive and negative charge. Because any test charge I drop in here, any little tiny point charge that I drop in here is going to experience, remember it's a positive test charge, it's going to be repelled by this positive charge to the right, it's going to be attracted by this negative charge to the right. So the electric field and thus the electric force everywhere on this line will be to the right. Right, so let's erase that little test charge. We'll draw the field line back in. So that's one field line. Now, The closer we are to the positive charge and the closer we are to the negative charge, the stronger the electric field. Because remember, it goes as 1 over r squared, the distance from those charges. So the next set of lines will look something like this. See how they're slightly curved. So if you place a positive test charge here, it's going to feel a push mainly from this positive charge up and to the right, a little bit of a pull from the negative charge to the down and to the right. But you're much further away from this negative charge, therefore the electric field contribution from that negative charge is weaker. Drawing in the rest of the field lines now. Might look something like this. Oops. Do better on this last one. See how they're all originating from the positive charge, they're all terminating at the negative charge. So the line that comes out here, I would have to draw up and around on top of the wall here, and it will come back down and terminate at the negative charge over there. I just can't draw the loop that big. This charge here, same way, the loop comes in and will come back over here. These 3 loops correspond to these 3 entry points here. And that gives us our approximate electric field around a dipole. So of course a positive test charge placed here would feel a push to the left from the positive charge. It would feel attracted to the right from the negative charge, but the negative charge is further away. So a positive test charge would be pushed to the left. This line goes to infinity to my right, comes back around from infinity to the negative charge. So we have here the electric field lines around a dipole. Notice that where the electric field is spaced far apart, the field is weaker than when the lines are closer together. Notice how the lines do not overlap in any fashion, because electric field lines cannot overlap. Notice how they're all originating from the positive charge and they're all terminating at the negative charge. I'm not drawing a field starting in the middle of nothing and having it go somewhere. It can't do that. So look over your book and look over examples you can find online. Just type electric field line examples, and you'll see the electric field examples for various configurations of charges. This is a nice symmetric version for a dipole. If I threw another charge in here, another positive or negative charge, the field lines would all shift, so they would still follow the rules that we explained earlier. None would overlap. All field lines would originate at positive charges, terminate at negative charges, but the symmetry would disappear. So this is the electric field lines for a dipole.